Imagine a robot needing to navigate a busy factory floor, or even just cross a room, without bumping into anything or anyone. How does it instinctively know the best way to get from point A to point B? It seems like magic, but behind every smooth and safe robotic movement lies a sophisticated system that thinks ahead. Robot path planning algorithms are the computational methods that enable a robot to find an optimal or safe path from a starting configuration to a target configuration. They achieve this by systematically analyzing the robot's environment, avoiding collisions, and respecting its physical and dynamic limitations. The core mechanism behind these algorithms involves understanding the robot's world in what is called configuration space, or C-space. Think of C-space as a multidimensional map where every possible position and orientation of the robot is represented as a single point. Obstacles in the real world translate into forbidden regions within this C-space. The algorithm's job is to find a clear path through the free C-space. For simpler environments, graph-based search algorithms like a star or Dijkstra's can discretize this space and find the shortest path. For more complex, high-dimensional spaces, especially with many degrees of freedom, sampling-based methods like rapidly exploring random trees, or RRT, and probabilistic roadmaps, or PRM, become essential. These methods randomly sample points in the free space and connect them to build a navigable roadmap or tree, which is then searched for a viable path. In practice, these algorithms take the robot's current location, its target destination, and a map of the environment as input. The map might be static, meaning unchanging, or dynamic, adapting to moving obstacles. The algorithm then outputs a series of waypoints or a continuous trajectory that the robot's motion controller can follow. This process often involves considering the robot's kinematic constraints, which define its movement capabilities, and its dynamic constraints, which relate to its speed and acceleration limits. A fascinating aspect often incorporated into advanced path planning is the concept of cost functions. Instead of just finding any path, many algorithms aim to find the path that minimizes a specific cost, such as travel time, energy consumption, or even the amount of wear and tear on the robot's joints. This allows for truly optimized movement beyond simple collision avoidance, sometimes even incorporating social costs to avoid moving too close to humans. The choice between a complete algorithm, which guarantees finding a path if one exists, and a probabilistically complete algorithm, which is highly likely to find one in complex spaces, is a key design decision. Ultimately, path planning algorithms transform a complex navigation problem into a computable search or optimization task, ensuring robots can operate autonomously and efficiently. By understanding how these algorithms map the world, identify obstacles, and calculate trajectories, we gain insight into the foundational intelligence that drives robotic movement and decision-making.
If you love robotics, like, subscribe, and keep building with us.